So today's lecture is going to be on phase transitions. As I have said, phase transition is one of the most important and interesting topics. Today's lecture will be basic introduction to phases. What exactly is a phase? How to define phase diagram, and then start thinking about what is phase transition. It will be a very basic and introductory lecture, so not much technical details, with not much technical details, but as much technical details is required, I'm going to discuss. So first, let's start from the fact. First, let's ask what is a phase. We all know, for example, so I'll be actually following a very nice lecture note by Matthew Swartz. This is a lecture note that I'll share with you. So let's start with what exactly is a phase. So, we know so there are we are familiar from solid, liquid, gas, for example, water, ice, and the vapor. These are different things about the same things, same object in three different regions of temperature, etc. And these are different phases. Okay. So there's a solid phase, liquid phase, and gaseous phase. There are plenty of examples. For example, for carbon dioxide, for gases, if you take carbon dioxide, you decrease the temperature, increase pressure or something, it will solidify, or it will become liquid. So these are the phases we are familiar with. Water is the simplest examples that we look at every day. There is another phase that generally we have heard about, are called plasma, which are ionized gas, but we will not be talking about them. They appear in various places like sun, etc., etc. But you can read a little bit from here. There are other important phases. Those are for example, that appear in magnet. For example, ferromagnet, paramagnet, diamagnet, etc., which all of you have heard about. Then there are phases which are conductors, insulator, semiconductor. These are phases of matter. Then there are phases which are very exotic phases, which are very important, are something called quark-gluon plasma. There's a quark-gluon phase. If you take nuclei, and break it apart by in LHC, people do experiment. They take two nuclei and then they just smash them against each other. Inside this, I have so inside I have generally the quarks, and the quarks they are bound together by gluons, etc. If you smash them, you suddenly get a phase where you see quark and the gluons all there. This is also another very exotic phase which appears. Okay. For example, in black hole, there is a phase. There are different kind of phases in black hole, and solids do have various phases. To give an example here, carbon, it gives you diamond. If you put the carbons in a particular pattern, suppose you put some particular bonding, it becomes diamond, and then other bonding gives you graphite. So the phase of matter is a very common thing that we see. it just the same thing. We see it in different kind of configuration, and then those are different phases. Okay, this is a very common occurrence. Okay, study of phase transition is very important topic. Of course, we all see, had the phase transition suppose not happened, then with a refrigerator you won't be able to make water to a ice. So ice would appear independently as water. And the vapor, even if you keep on heating water, if there was no phase transition, water will always remain water. You won't get any vapor. So phase transition is also fact of life. And also very important. And maybe as you can see, suppose you can make a phase transition from graphite to diamond, you become rich. So phases are important, phase transitions are important, and it happens all the time. We see all the time that is happening. So our aim would be to first actually characterize the phases a little better, understand them a little better, phase transitions, characterize the phase boundaries, how to go from one phase to the other, those things better, and try to understand this phase transition. This is what we are going to do in today's lecture. By doing better, meaning we need to understand them mathematically. We understand, we see, but we need to put some equations. And why do we need to put some equations? It is going to give us more intuition, so that that's how we make progress. We understand them more physics wise, and then we can use them to do something new. So that's that. So our aim would be to understand these phases with some mathematical equations, and try to describe the phase transition, the phase boundary, the phases, etc., etc. Okay. So, for example, we would like to understand whether two phases coexist. And then we would like to understand, of course, the phase transition occurs. So then can the two phases coexist? Can three different phases coexist? Three phases coexist. Is there a possibility that there's no separation between two different phases? Is it possible that I cannot distinguish between two different phases? Distinction. I can see water and gas, water and vapor, water and ice. There is a distinction lost. Is it those things I can distinct? But is there a way maybe they lose their distinction? That I cannot really say, oh, this is water, this is gas. Is it possible? So these are the kind of questions that we will be discussing today. To make things more precise, let's start with definition of what is a phase. One can say maybe phase is a, as you say, some textbooks say phase is a uniform state of matter. But suppose I take gas, here very nicely explained. If I take a gas, and at different temperature, you will have different density, but it will have different uniform. So these are different uniform state of matter. But all of them are different phases. No, all of them are the gaseous phases, right? So you need a more precise version of it, and the precise version of the phase is that phase is a state of matter whose properties vary smoothly. That is, it's an analytic function of pressure, volume, temperature, etc. So so if I am in a same phase, pressure, volume, and temperature has to vary uniformly, smoothly. You might think, as this is written here, you might think that that makes a definition, that may not be able to distinguish between the liquid and the gaseous phase of water. Why? Slowly, suppose you start with the water and boil it, and then it slowly becomes the steam. if you look at temperature, temperature remains the same. Pressure remains the same. There's no change, right? Pressure is you are just doing an atmospheric pressure. Temperature is the temperature remains the same, 100 degree. So that's where the steam becomes. But what happens is that when we put temperature does not rise, but what happens is that something changes. Okay, as it is, we require something called latent heat, right? To go from one phase to other. So that's something which distinguishes between water and the gas. So we do require this thing, but there is another quantity that we can discuss is the density. So density at this temperature and density at this temperature will be different. So there will be a distinct, discontinuous change of density from this temperature to this temperature. Okay. So it looks like a very good definition that phase is a state of matter whose properties vary smoothly with respect to pressure, volume, temperature, etc. etc. So, and different phases then will be distinct by the fact that the properties will vary abruptly or discontinuously. That's much better definition. So this connecting. So you see how we are actually trying to do a mathematical theory of this phase and phase transition. First, we are saying, look, a phase is somewhere I can define with the smooth function of, I can define phase by, it has a smooth, whose property varies smoothly with respect to pressure, volume, and temperature. So definitely, I'm defining phase by some, pressure, volume, and temperature. Already, I'm putting some mathematical equations. Then I'm saying, look, if I want to change from one phase to the other, one to other, then this whatever function that I choose to describe, that has to vary, discontinuously. So already I'm trying to put in some mathematics to this, all these words that we know about phases and the phase transition. It turns out there are two different ways to people like to describe phase or phase transitions. One is what we just discussed, that suppose there are two phases, phase one and phase two. Here I describe certain quantities which are well defined, and here also again I define quantities which are well defined. If I want to go from one to the other, we'll see there will be a there will be a discontinuous transition, like discontinuity the density, etc., etc. Okay. The other is that there is more universal kind of description where you try to describe phase one and phase two together. These are one very interesting thing is called partition function that you will learn in your next semester, but we will not discuss here. And then there's a lot of thing about critical phenomena, etc., that start appearing, but we will not discuss this here. So, so we'll be just taking a very simple approach, which is I have within a particular phase, I define certain quantity. Another phase, I have another. I define other quantities. The quantities separately, and then they are there is a distinct there is a discontinuous change. Okay. Now let's try to our aim to understand things more in terms of mathematical terms. Let's try to distinguish between solid, liquid, and gas phases that we always see, like water appears in the solid phase, liquid phase, and the gas phase. So how do I distinguish between liquid and the gas, or the solid and the gas? So first, let's try to distinguish gases from liquid and the solids. We define some quantity called compressibility. It's just basically that if I change the pressure, how does the volume change? Okay, so this is the compressibility. As this is clear from this definition, if I have solid or liquid, I change the pressure, if there is no phase transition, let's say for the moment that I change the pressure, the volume of the solid or the liquid don't change. But if I change the pressure, volume of a gas changes. For example, if I take ideal gas, P is equal to nRT, if I calculate this beta T, it just goes as 1 over P. So this is not equal to 0. So you see, compressibility is something very nice which distinguishes between gas phase with the liquid and the solid. Okay. Then is there some way, but for the liquid and the solid, if I want to get a distinction between liquid or solid, compressibility is not good. Then there is something called shear modulus that you already know. Solid has a non-zero shear modulus. So under shear, under shear force, solid resist the shear force, right? So what is a shear force? Shear force is, you have something here, and it just that two different surfaces are going at two different velocity, and that is called shear. So solids do resist to the shear force. And so here solids and liquid, the same substance, often have approximately the same density, while the density of the gas is much lower. Liquid and solid are called matter. Solid differ from the liquids and the gases that they are rigid. More precisely, they do not deform under shear stress, that they are zero shear modulus. So the shear stress is an order parameter for liquid solid fusion. So liquids and gases are collectively called the fluids. Okay. So what I'm just trying to say is that the shear is something which actually can distinguish between what is shear, what is going to be your liquid versus what is going to be your solid. So it distinguishes between solid with the liquid or the gas. Okay. So compressibility distinguishes between compressibility distinguishes between gas with the liquid or the solid, and the shear distinguishes between solid or the liquid or the gas. Okay. There is one there is one important property that will be useful, is for example, if you have for liquids, there is a there's something called there is something called surface tension. Okay. So what is a surface tension? Suppose there is a surface of a liquid, there are molecules, and then there are molecules here, just like here. This is a water molecule. You see that this molecule here gets a bonding here and the bonding here, bonding here and the bonding here below. So roughly speaking, I'm going to very roughly I'm drawing, there are forces that are connecting between this are pulled from here and here and here and here. Roughly, there is no force in this layer, because equal number of them are pulling up and equal number of them are pulling down. But if you look at here on the surface, there is nothing to pull these things, right? So these bonds are dangling bonds. So just like here, these molecules here are dangling. Other things are there. So as a result, what happens, because these molecules, look at, they get a force which are you know, here they get an unequal force. So this results into a surface tension. So as a result, liquids, they form droplet, right? They don't occupy the full volume that is given to them. We see that I can that's how the droplets are formed, right? So these are the droplets, and then you can find out various liquids have different kind of the surface tension. Uh, so yeah, so yeah, we are just trying to understand various properties. So gas has compressibility, other things don't have. Here for solid, and we then distinguish the distinction between solid and the gas and the liquids are can be done by the shear modulus. And then we saw that the liquids do have their own surface tension. So these are the various properties by which you can distinctly say about various phases, right? So the thing was here that we wanted to characterize the phases, okay, various phases, okay. Okay, so we'll now uh, you might have seen the following, and actually we'll come and discuss this better, more. Let's try to understand some more thing. Suppose there is water here, and there is water molecule that is there, and suppose this is a closed container, okay, and these are vapor molecule. So if I have a closed water bottle, it will not be only it will not be just the water. There will also be vapor. Best way to see this is you put it in the you often see that upper part of the bottle. If you go to the AC room, you see some cloudy kind of thing, right? So always there is water and the vapor. They will coexist in this water. If I have a closed water bottle, if you open the water bottle, eventually all the water will sometime it will evaporate, right? You put the water on a surface, slowly the water evaporates. If the water do not evaporate, then mopping does not work. Then all your effort to mop a surface will go to the vein. So it's a fact of life that the water evaporates. All of you know that. So and in a closed water bottle, what might happen? Interestingly, we'll see them again. That let's say the water molecule evaporates, and then it bounces back to the surface and comes back again. Okay, and or the rate at which water molecule evaporates, at the same rate the vapors do come back, right? So in a closed container that often happens, and this kind of equilibrium can exist, okay. So water and the gas or the vapor can coexist with a perfect equilibrium. That's why we see, if I keep a water bottle with water, generally packaging works, they are there. You can keep them for 6 months, 1 year, they are there. But if you as I said, if you just drop that water on the surface, a bigger surface, it will just evaporate, right? Because it has got the open air. It has it will slowly evaporate, and it will find nothing. So what we see is that if I want to distinguish between water and the vapor, volume and temperature together may not be a very good choice, because I just give you an example. where water and the vapor are changing with each other, mixing, going from one to the other, and the volume and the temperature is not changing because I have kept the water bottle in a particular temperature and the pressure is, the water and the volume is the same, right? So in generally, that's not a very good measure of a distinction between a phase, two different phases. I can have, with the same volume, I can have, and the temperature, I can have water and the gas. So, there is no way I can distinguish. So, this is, suppose I tell you, look, this is the volume and this is the temperature. Can you tell me whether this is a press, whether this is a gas or, gas or the liquid? This is not a very good question. So, but rather, what is a good question is that I distinguish the pressure. I try to understand the phase with respect to the pressure and the temperature. Okay, I'll come to why that's a better way to describe a phase. So what I just said here is written here, that why the volume and the temperature is not a very good way to describing a phase, but the pressure and the is not a good way to characterize. But the pressure and the temperature is a good way to characterize a system. Okay. Now let's try to. We have you have seen what is a phase diagram. I'm going to come to what exactly is a phase diagram, how to draw them, how to find out their equation, etc. Will come, but you know that you have seen kind of this picture. This is a solid phase. This is gaseous phase. This is gaseous phase, and this is the liquid phase. Okay. You have seen this kind of picture. This is called phase diagram. Okay. I'll come to more precise thing about this phase diagram. So you see, there's a solid phase. For example, this will be ice, this will be water, and this will be vapor. The solid to liquid phase, this goes on. You keep on increasing, pressure and the temperature. Keep on increasing pressure. It will go on. For gas and liquid, it will stop somewhere here. I'll talk about it. This something called critical point. And at this point, you see, you won't be able to distinguish between liquid and the gas phase. So pressure and temperature is a very nice way to distinguish between, your different phases. We'll actually describe them. So let me first show you a phase diagram for three different things. So this is for carbon dioxide. Okay. Let's look at this. One atmosphere is our atmospheric pressure, and 300 degree Kelvin is like 27 degrees centigrade, which is like the room temperature, 25 degree temperature. Carbon dioxide is a gas at room temperature and the atmospheric pressure, and that's why you see this is the gas, right? This is the gaseous phase. Now, what happens is that if you decrease the temperature, suddenly this carbon dioxide will become solid. That's why, sometime often you see that, gas comes out of, solid. If you look at solidified, carbon dioxide, the gas directly comes out of here, because, there's this is the thing, So this line, this distinguishes between gas and the solid, and this is called sublimation curve. Okay, this is some name. But if you increase the pressure with the temperature, suddenly you will see that carbon dioxide has become liquid, and again, suppose you are here, if you keep on increasing the temperature, sorry, if you keep on increasing the pressure, it will become solid. That is acceptable, right? You are basically compressing and compressing, you are increasing the pressure, and then suddenly, uh, uh, very rough intuition is that if you're increasing the pressure, more and more molecules are coming very close by each other, and then slowly, you're trying to, they make a solid. Okay, so that's basically the rough intuition. So you see, there's gas phase, there's a solid phase, there is a liquid phase, and this is a very interesting point. This is so along this line, you see two phases coexist, right? This is a coexistence line. Liquid and the gas phase, they coexist. Along this line, there's a liquid and the gas phase coexist. This is a very interesting point. Solid, liquid, and gas, all of them coexist along this at this point. This is a triple point. This is another very interesting point. This is the critical point. You see that the fact that the liquid and the solid, they keep on going, they don't stop. Okay, you distinguish between liquid and the solid. There's a distinction between liquid and the solid. But at the critical point, you see the gas phase and the liquid phase, they no longer can be separated. In fact, there is this region, okay, there's this supercritical region where gaseous phase and the liquid phase are not distinct. Okay. So I will actually attach a video where this experiment can be seen. For example, okay, so I'll talk about the video in a minute. Let's look at the argon. In the argon is also a very similar picture, as you can see here. It's not, it's just you can understand now what is this picture means. So this is a phase diagram. Okay, these are the phase line, the boundary of the phases, etc., etc. Now let's look at our favorite water. At the atmospheric pressure, you see the water is liquid, right? That's what we see. And the atmospheric pressure and the room temperature is a liquid. It's not solid. It's not ice, right? You have to decrease the temperature to get the solid. Very interestingly, again, there is a triple point. Every one of them has a triple point, right? This is so interesting. There's a gaseous phase, there's a solid phase, there is a liquid phase, and there's a critical point. Why don't we see the critical point? Or why don't we see the triple point? Because water is always available. Why don't we see it in our day-to-day life? What does the meaning of triple point means? Triple point means that water, liquid. So water, the liquid phase, the gaseous phase, and the solid phase, they will coexist. What does it mean? It will mean that there will be ice as well as the water as well as the gas. Bubbles will come up. Well, in our home, we have seen if we actually heat, the bubbles come out, right? This is this, and then if I take out the heat, the liquid becomes solid. That's what we see, refrigeration. And here to here we have seen, right? By increasing the temperature. Suppose I'm here. I decrease the temperature, I go to the solid. I increase the temperature, I go to the gas. These are the things I have seen, but we have not seen this. Even though this is like the room temperature, the point is that the pressure that is required is very, very low. So I won't be able to see this. You have to do an experiment to see this, and you can do that experiment. Well, let's come to the critical point. So the critical point is where you stop distinguishing between gas and the water. You can say how? How is it possible that, if there is a water, suppose I have a water bottle, suppose there is a water bottle, there's a water and there is a gas. I can distinctly see that, what is the meaning of, what is the meaning of, I don't, in our usual day-to-day life, I don't see this critical point. Very interestingly, what you can do is that you can take water and then increase the temperature go to this temperature and increase the pressure up to 10 to the power 10 100 atmospheric pressure or something, and you will start seeing that the distinction between the water and the vapor just goes away. It's a very beautiful thing. So what I have done to emphasize this point, I have also attached a video with this lecture, which describes for you, which is a demonstration. It's a video of a live demonstration. It's as a 3-4 minute of video. What you can see, what exactly is the meaning of trickle point? Okay, you can see that the water, ice, and the gas, they coexist. And the critical point, they do the experiment. They slowly they take container, they put a water. You initially can distinguish between water and the vapor, and then slowly increase the temperature and the pressure, and then suddenly you see that the distinction is gone. Okay, you see the critical point. Look at those two videos. It's really nice. Okay, and these are the phase boundaries. Question is, how do I find out phase boundaries? Right? I know if I have very high temperature, water will be in the gas form. Well, actually that's not an absolute statement. If I'm in a very high temperature, that's our usual notion, because that's what we see in our day-to-day life. The point is that if I also increase the pressure, suddenly actually with that temperature, it can become liquid water, right? That's what. So there's a very beautiful interplay between pressure and the temperature. And so how do I figure this out? How do I figure this line out? Okay, how do I figure this line out? So that's a very important thing. That is what we want to understand. This phase boundaries, how do I figure this out? As you can understand, so at any point here, this everywhere here, this is a gaseous phase, and any point here, or here is an equilibrium point. Okay, what do I mean by equilibrium point? That at that point, pressure and temperature keep fixed. And I know, if it's an equilibrium point, you can check that at that point the Gibbs free energy is minimized, right? So last time, if you remember, at a constant temperature and the pressure, delta G is 0, right? Delta G less than is equal to 0. That's what the equilibrium condition we figured out. That delta G has to be, by second law of thermodynamics, delta G at constant temperature and pressure, the most important quantity is the Gibbs free energy, and the Gibbs free energy has to be less than is equal to 0. You see, this phase diagram, drawing this, understanding what variable I should draw the phase diagram in, already tells that which thermodynamic potential I should be thinking about. And the best thing is the Gibbs free energy. Okay. So each point on this plot is a equilibrium point. Okay. Now we would like to do a we would like to understand things a bit from mathematics perspective. So first question that we would like to understand is, how do I find out this phase boundary? Okay. As you can see, in this phase boundary, there are two different things exist: gas and the liquid. Okay. So let's look at one particular point in this phase boundary. Let's say this point. Imagine this point, right? In this point, there exist both gas and the liquid. Their pressure and the temperature are fixed. But what can vary is the number density of the gas, the number of the gas molecule, and the number of the what molecule, or the chemical potential of the they need not be the same. Okay. Basically, I have fixed in this diagram, all I have shown you is that the pressure versus temperature. So at this particular point, what can be different is pressure and the temperature in the gas in this line is the same at this point, But what can be different is the chemical potential can be different, you know. So I have not really fixed them. So we'll see. So suppose at that point, at this point, there is a mixture, gas and the liquid mixture. So let's try to first understand if there are mixture of two different phases. Let's say one come with the suppose one come with the N1 number of molecule with the mu1 chemical potential, the other come with the N2 number of molecule with the mu2 potential. Then as we have discussed, the Gibbs free energy is the best quantity because, you know, I'm looking at temperature and the pressure are the important variables. So dG is equal to VdP minus HdT plus mu1 dN1 plus mu2 dN2. Look at the previous lecture if you have forgotten where it comes from. So at a constant temperature and pressure, suppose I take pressure and temperature to be constant. So dG becomes mu1 dO1 plus mu2 dN2, right? dt is 0, dP is 0. And let's say I'm thinking about a container. I have fixed the temperature and pressure. And, you know, what happens is that there's a water and then there's a gas. Let's say the number of molecule goes up. So from water phase to the vapor phase, let's say delta N changes in the water phase. So in the water, dN1 is equal to minus dN2 because the delta N will become vapor, right? So vapor will gain the number, water will lose the number. So let's come from phase 1 and phase 2. In the phase 1, dN1 is equal to minus delta N because there is a change in the number, and phase 2 there's a delta N gain. So mu2 minus mu1 delta N, right? Now, the principle of equilibrium says that I need to minimize delta G. So in order to minimize the delta G, particles has to move from higher chemical potential to the lower chemical potential, right? If, you know, so mu2 has to become close to mu1. Okay? If I have, you know, if I have, let's say, but let's say mu1 is not same as mu2, right? Chemical potential of two different substances are different. So then whatever has more chemical potential or whatever has lower chemical potential, the phase will be of that thing, right? So what do I mean by that? Suppose given a temperature and chemical potential, given a temperature and the pressure, if you know, I wanted to mix two, yeah. So here it is written that's at a fixed value of temperature and pressure, as long as mu1 not is equal to mu2. You know, if mu1 not is equal to mu2, then I see that delta G is not in equilibrium, right? But then as long as mu1 not is equal to mu2, you know, so what happens? Sorry. So let's see. So in this phase, let's say I'm here. Okay. What I want to say is that let's say I'm here. Let's say I'm in the gaseous phase. In the gaseous phase, this is going to be stable gaseous phase. In the gaseous phase, okay. So what I want to say is the following: that, you know, this line will be dictated by where mu1 is equal to mu2. Okay. Because what I really want in this phase diagram is that every point is what I want it to be at equilibrium. And at this point, let's say mu1, at this point, I know there are two things, right? There is a gas as well as the liquid, right? Both together. So at this point, if delta G has to be minimum, so mu1 has to be same as mu2. And in fact, this line is the line where if I look at the chemical potential of liquid and chemical potential of the gas, with, if I change pressure and temperature, if along what line mu1 remains same as mu2, that is this line, okay? In this line, in these points, chemical potential of the gas is totally different than the chemical potential of the liquid. And at this temperature, you can show that chemical potential only along this line, the chemical potential of the gas and the liquid, they are exactly the same. Okay. So that's all I wanted to say, is that just follows from here. That just follows from here. That just follows from here that if there are two different phases that coexist, if the Gibbs free energy has to be has to take the lowest value, minimum value, mu1 has to be same as mu2. Only then two phases will coexist, right? Because the Gibbs free energy will then be minimized. And I see already we see if mu1 not is equal to mu2, then Gibbs free energy cannot be minimized, right? Because then it's just positive, like I keep on increasing delta n, then Gibbs free energy keep on increasing, right? So so what happens is basically that, let's say I get two phases where there are mu2 not is equal to mu1. So what will happen is that what happens is that Gibbs free energy. Because this is non-zero, what will happen is that either liquid or the gas, they cannot coexist. Either only one of them is going to exist. I think I should explain this better, but already it's a little, maybe I'm already 40-50 minutes over. So I maybe next class I have to discuss this. I need to discuss this a little better. But what I wanted to say here is let's take one take home message is that in order delta G to be minimized, mu1 has to be same as mu2, and these phase boundaries are exactly determined by mu1 is equal to mu2 line. Okay. Or for the case of liquid or the solid, these are mu1 is equal to mu2 line. Okay. So that is what is being discussed here. Mu1 is equal to mu2, that there is no change in the Gibbs free energy with delta n, and so only then the two phases can be present at once. Okay. Since mu1 and mu2 are functions, setting them equal generates a curve in mu2 plane. So as you can see, mu1 is a function of T and P, mu2 is a function of T and P. Two different molecules, two different phases has different mu1 and different mu2. And if I set them equal, I'll get an equation on T and P, right? So let's say mu1 is equal to T to the power P1, T to the power A1, P to the power B1, and mu2 is equal to T to the power A2, P to the power B2. Then mu1 is equal to mu2 would imply T to the power A1 minus A2, P to the power B1 minus B2 is equal to 1, right? and this is a curve in the PT plane, right? That is what this is. Okay. Okay. So we have found what is a phase boundary. We need to discuss about what is a critical point, what is a triple point, etc., etc. That I think I'm going to discuss it in the next lecture. Okay, so this went a little slower than I thought. Okay, anyway, so this week what I'm going to do is actually going to rather than the tutorial, I think I'm going to take one extra, well, not extra, but instead of the tutorial, I'm going to take a lecture, maybe, depending on, because otherwise there is no problem set that I can give. Yeah, okay. So on Thursday, maybe I'll, instead of a problem set, I'm going to give a lecture, okay? Thank you.